Okay, so now we're recording. All right. So this was a midterm exam question that was asked in the fall, um, and I'll just read it because it looks a little pixelated on my screen, so it might be hard to read. Um, but you have been tasked with performing a tolerance analysis on a vendor-supplied spark plug. Some of the plugs have been causing misfires, and your company wants to know if it is a mechanical or an electrical issue. Thankfully, your vendor has supplied sizes and tolerances for all parts. Um, and so we're asked to first set up the equation for your tolerance loop. Second is determine the minimum and maximum gap expected from your tolerance. And third, we're told that the gap must be between 5 and 1.5 millimeters to protect proper function. And so we're asked if we need to make changes, what changes will we make in the component dimensions and their tolerances. And so we're given the spark plug here, and then we're given some of the key dimensions. And so if you think back to the lecture, the sort of different types of problems that you might encounter in dealing with tolerance loops, this is one where you basically know all of the nominal dimensions and you know the tolerances, and you're trying to preserve a critical function. I think it's the second type. So you're trying to preserve a critical function, which is the ability of this spark plug to generate a spark across this gap. And for it to do that, the gap has to be between 0.5 and 1.5 millimeters. And so that's sort of the critical function that we're attempting to preserve, is the length of the spark plug gap. And, you know, for those of you guys who have tinkered around with internal combustion engines, oh, okay, cool. Yeah, I did post this on Canvas, so it looks like, yeah, cool, thanks. Carlos just shared it with everybody. Awesome. I probably should have done that. Good thinking. Okay. Yeah, so it's the same problem that's posted on Canvas. I don't have the solution yet up on Canvas because I wanted to walk through it here before everybody saw the solution. But we'll put the solution up after class is over. So for those of you guys who have messed with internal combustion engines, or who have even, you know, taken thermo, this is kind of a cool problem because if you remember, there's a bunch of power cycles, right? There's the Brayton cycle, the Stirling cycle, the Rankine cycle, the diesel cycle, the Otto cycle. Diesel and Otto are internal combustion cycles, and the Otto cycle, which is the one that's based on, or the one that automotive engines are typically based on, you do not manage to compress the combination of the air and the fuel to its auto ignition temperature and pressure. And so you need a spark to cause the combustion process to occur. And the spark is generated by a spark plug, which is represented schematically here. And if the spark plug is set wrong, the spark will either, this gap is too small and the spark will happen, but the gap isn't big enough for the flame to propagate, right? So nothing gets set on fire if the gap is too small. And then conversely, if the gap is too big, there isn't enough voltage to push the spark from the core over into the housing of the spark plug. No spark will jump, and so there's no combustion process. And so either way, you can get a misfire unless the spark plug gap is dialed in precisely from 1.5 to 0.5 millimeters. So that's sort of the background of this. Okay, so the place to start then is with the tolerance loop template, which, let me see if I can get it all on the screen. There we go. Okay, so this is a tolerance loop template. I've put on Canvas both a Excel version of it, which is editable, and kind of a blank PDF version of it, which is sort of editable, but not nearly so much. The blank PDF version is useful, like in this case, if you've got the drawing already, you can drop the drawing in to the blank PDF version and just print it, and it's very easy to use. Otherwise, you sort of have to draw it in. But if you want to, you know, put things in advance, you can using the Excel version. So those are both uploaded now onto Canvas. Okay, so there's multiple steps that have to be done in order to get the correct equation for the tolerance loop. But the very first thing is to use the template, right? So that's step one, is to use the template. And step two is to have a drawing here that's representative of the part. So there's my drawing. And the reason that I picked this particular problem to start out with is because the people who wrote this problem, which would have been me and Dr. Nemi about a year ago, were very kind in kind of identifying what each part is, and then how the parts all stack up in the assembly. And so we set the coordinate system because tolerance loops are basically just sums of vectors. So I've got a one of the asynchronous videos describes kind of the underpinning math that underpins how tolerance loops work. And since they're all vectors, the first thing that you have to do is set a coordinate system. And so we're going to set this as our 0, our datum. Oh wow. Okay, I was going to say yikes. That's red ink. It doesn't look red here. Now it looks red. Okay, so we're going to set our datum right here. So that's going to be r equals 0, and then the positive r direction is going to be, well, at least what is to my left. I hope it is also to everyone else's left. If not, you're looking at a flipped version of the picture. So to my left. And that's important, as we'll see in a second, because it tells us as we're adding the vectors together whether we need to add them together or subtract them from one another. So we've got that set. And then once we've got that starting point set, the thing that we want to do is just add the vectors together until they sum to 0. And so what vectors am I talking about? Okay, well, I'm talking about the vectors associated with how all these parts stack up with one another. And so, for example, if I've set this as my 0, let me just draw this line down here. If I've set this as my 0, it's very natural to start with the terminal as the first vector, and the terminal is this part here, right? So this is the terminal. So if I start with the terminal and draw my vector, we'll call that vector t. So that's the first one. And then I want to go from the terminal into the core. The core is this big white section here, right? And so we've got sort of a hint that that's the vector associated with the core. So I'm going to draw, there we go. I'm going to draw a second vector there in the core. And then the third vector that I need is the one that's associated with this gap, right? That's the critical dimension that I need to preserve. And so I'm going to draw my third dimension across the gap. And now the gap is basically an air gap that separates the core from the housing. So now I'm at the housing. And if I go any farther to the left, well, there's nothing to the left, right? Like the part ends or the assembly ends. And so I then have to turn around and go back to the right. And so I'm going to go back now. I'm in the housing, right? The housing is this black part. I'm not going to draw inside the housing, because if I draw inside the housing, my pen will disappear. So I'm going to draw, let's see, back through the housing, and where the housing ends is right here, which is where the seal is. So let me draw it, and then we'll see if I can explain it better. So I'm going to draw all the way back to this location. And the reason that I pick that location is because that's where the housing and the seal, which is this little gray part here, interact with each other. And the interaction is in the other direction. It's to the left instead of to the right. And so I'm going to draw a little arrow inside the seal. And I'm going to draw my final arrow, which is going to be associated with the insulator, which is this gray guy. I'm going to draw him out here, because otherwise it's going to get too messy. Okay, so, and that was sort of hinted at, right? That whole process was hinted at, because I started here. And if you look down, let me change colors to green now. If I start down here at my datum, the vector loop that I drew matches the vector loop that's sort of already on the drawing, right? So I go from the terminal through the core, across the gap, change directions, go across the housing, and then the housing interfaces with the seal, and then the seal interfaces with the insulator, and I get back to where I started. So a couple of sort of key features of this. First is that I have to have a return path, right? So I start from 0 and I have to end at 0. So my start was right here and my end was right here. And that's key because ultimately these are vectors. And so when I sum them up, I want the sum of all the vectors to be 0. So that's one key thing. The other key thing, I tried to represent it here, is that these vectors are essentially drawn head to tail or tail to head, right? So within the insulator, I started at the end of the vector and I moved up to the head of the vector. And then I started from that point to draw the core vector. And then I started from the head of the core vector to draw the gap vector. And then even though I changed directions from the gap vector, I drew all the way back from that same spot through the housing. And then the seal starts at the same place that the housing ends. And then the insulator starts where the seal ends, right? So these are all meant to be, if I kind of represent this, you know, down here, they're meant to be just a series of vectors that run from head to tail to head to tail to head to tail and so forth. And so ultimately, though, I have to get back to the origin. So those are the two things that I wanted to point out. Once I've got those vectors drawn, the next thing that I can do is write the equation to sum them up. But let me pause here for a second and ask if anyone has questions about how I drew the vectors. Not yet. Okay. The questions will come, I am certain, because how setting up these problems and drawing the vectors is actually the hardest part. So once you've got this drawn, if you've got it drawn correctly, the rest of the math is relatively simple. Okay, so I'm gonna name each of the vectors, and then I'm going to put in the nominal dimension and the tolerance. So the vectors, I'm just going to name them by letters. So in the terminal, I'm going to call that T. And then if I move on to the core, I'm going to call that vector C. And then I'm going to go through the gap. I'm going to call that vector G. And then I run through the housing, that's vector H. And then I'm going to interface with the seal, that's vector S. And then ultimately I have to go through the insulator, and that's vector I. And remember, I've got the nominal dimensions and some of the tolerances from the problem statement. So let me see here. Hopefully you'll trust me to copy them correctly. So the terminal is 13 millimeters, and the tolerances are 0.065 in the plus and 0.065 in the minus direction. The seal is 5 millimeters. Put the units on here, 5 millimeters. And it's 0.025 in the plus and 0.025 in the minus directions. The insulator is 25 millimeters, and it is 0.115 in the plus and 0.115 in the minus. These are all bilateral dimensions, right? So it's the same on the top side as it is on the bottom side. Now here's where things change. So here's the core. 44 millimeters is the nominal dimension, and 0.220 is the unilateral dimension on the positive side, and 0.000 is the unilateral dimension on the negative side. So this core is very slightly different than the other components in that it has different dimensions in the plus and the minus. So those are called unilateral dimensions as opposed to everything else, which is bilateral dimensions. Okay, the gap, I'm going to leave this for now as just the variable G, and you guys will see why in a second. And I'm not going to worry about the tolerances on G. because it's this that we're trying to preserve. So this type of problem, if you've got a critical functional dimension that you're trying to preserve, you just leave it as a variable, and you'll see in a second, we'll solve for it. And then H is the housing, so this is going to be 40 millimeters, and it's a bilateral dimension, so 0.200 and 0.200. Okay, so let me bring this back here, and you can sort of compare, right? So terminal is 13, and seal is 5, and insulator is, oops, good thing we checked, because the insulator should be 23. Yeah, exactly. Thanks. 23, that would have been a disaster. Okay, 23, good thing we checked. The core is 44, and the housing is 40. Okay, anyone else see any errors in how I've copied things? No, okay, I think we're okay. All right, and so you can sort of see, right, this template is meant to be just a way to keep all the information that you need in one place, so it's easy to refer to. Okay, so we've got this filled out. For references, I'm not going to fill in references because they're all just given in the problem statement, but in some cases, if you're dealing with a problem where you've looked up a standard, a specification, for example, machinist handbook, one of the ANSI standards, and you need to know where the nominal dimension or where the tolerance of that dimension came from, you can write it here in the reference section so that you can remind yourself of where that came from. Okay, so now let me sneak down here, and we'll just write these out. So remember, we've got, and now here, let me zoom out just a little bit so that you can see the whole page. We don't need to see the writing so clearly as we did before. Okay, but it's important for you guys to see the directions. All right, so so I'm going to write these out. And the way that I would write them is I'm going to write just in order, so the same order that I did here. So I'm going to have T, which is the terminal, and I'm using, you know what I should probably do, instead of using a hat, let me just use a line. There we go. Okay, they're vectors. So T plus C, also a vector, plus G, also a vector. Now, the reason that I'm adding them, and let me even put a plus sign here just to be clear, the reason that I'm adding them up is because I started from my datum, right, my R equals 0, and I'm moving to the left, which is the positive direction, right? Remember, this is the positive direction. So this is added to this, added to this. But now when I get to the housing, what do? The housing, H, is a vector that goes in the opposite direction, right? So instead of adding it, I have to subtract it because it's going in the other direction, against the direction of my positive unit system. So this is going to be minus H, and then let's see, I add the seal. So now the seal, I go back in the direction that I started in. So it's going to be plus S. And then when I get to the end of the seal, I go back to the insulator, which is in the minus direction. So minus I. You start to get a sense that it's super important how you set this up. Okay. and that's it. So that's my vector sum, right, where I've taken into account the pluses and the minuses based on which direction the vectors are going. Still, of course, my goal is to solve for this gap. so we'll get there in a bit. Okay, the next step is to add the tolerances. And the way that tolerances are represented in the drawings is a little misleading. They're actually represented as little curves. And those curves are supposed to be just something that's so small that it's several orders of magnitude smaller than the actual drawing. The challenge with this, as you guys will see in a second, so here's a terminal, and I'm going to draw my tolerance in the terminal, and here's my tolerance in the core, and here's my tolerance in G, and here's my tolerance in the housing, and here's my tolerance in the seal, and then here's my tolerance in the insulator to get me back. So having just added those, the problem is these look very loopy, right? They look like loops, even though they're not. They're just meant to be tolerances. But a lot of times people will see this and they'll be like, oh, you drew the tolerance loops. And they're actually referring to the actual tolerances themselves, which look like loops, but they're not. The tolerance loop itself is the entire pathway from the start all the way through back to the origin. So that's the loop. These little loopy things are just meant to represent the tolerances, and they're just loopy because they're too small to represent as lines on the drawing. I'm not thrilled with this notation, but it's the notation that's been used in industry to do this for years, and so that's what we're stuck with. So I've got those in there now, and all that I've done in drawing those tolerance loops is I've just tried to connect the head of one vector with the tail of the next one, right? So that is a connection there, that's a connection there, that's a connection there, here's the connection there, and so forth. So just to sort of keep track of things. Okay, so now that I've got those drawn on there, and I've got my equation, the next step is to bring the tolerances into the equation. And I have a very sort of systematic way of doing this, which even though it's a little cumbersome and systematic, I suggest, at least in the beginning, that you guys use it. Because if you try to do this just off the top of your head, it gets very, very complex very quickly. So what I'll do is I'll just write each one of these vectors. I'll preserve the positive or the negative sign in front of them, and I'll represent the tolerances as basically a bilateral dimension, so or a bilateral tolerance, so plus and minus. So what I mean by this is if I write T, the units of, not the units, the tolerance of T is plus or minus delta T, and I put that in parentheses, and then C is plus or minus delta C, and then G is plus or minus delta G, and then H, I have to be careful because H is negative, so it's going to be H plus or minus delta H, right? Negative because the negative sign there, and then S is plus or minus delta S, and then I've got to be careful because I has a negative sign in front of it, I plus or minus delta I. And this all equals 0. Okay, now notice I did a kind of a subtle thing here. I dropped the vector notation, and I did that on purpose because these are all now just in a line, right? They're just all vectors in my R direction. And so I don't really need to account for the fact anymore that they're vectors. I just need to know what their signs are sitting in front of them. And I've transposed the signs down from here to here. So that was sort of subtle, but I dropped the vector notation on purpose. Okay, so the next thing I'm going to do, and this is the part that like feels like it's super tedious, is I am going to I'm going to drop the vector notation. Okay, and I'm looking at my solution. Sorry, I just did drop the vector notation. I'm gonna copy this 3 times, and I'm looking at my solution and I'm noticing that I've done something that's unexpected. Why did I do that? Huh. Oh, I know why I did it. Okay, all right, I'm back. Okay, sorry. I did something that was like, why did I do that? And now I know why. Okay, so I'm just going to copy this a couple more times, and you'll see why in a second. So plus or minus T, C plus or minus delta C. And this is the part that I was talking about before that's like, Trom, why are you doing this? It's so cumbersome. But at least in the beginning, I think it's important to see it done in all of its glory and all of its steps, to kind of preserve understanding of how this stuff works. And once you guys get good at this, after you practice it, you won't have to do this. But for now, at least, let's just do it as completely as possible so that you can see why things are the way they are. Okay, so I basically got three. Let's just number them: 1, 2, and 3. Okay, so for for 1, I'm just going to leave it the way that it is, because that's just going to remind me that I wrote that line. Number 2, I'm going to try to solve this for G min. And so what I'm going to do, and I've written this in pen, so I can't quite change it, but what I'm going to do is I'm going to focus on G here for a second. So here's G, and G min, remember that my G runs from, it can be as small as 0.5 and as big as 1.5. So I'm actually going to pull this out and I'm going to stick it over here. So if I subtract this vector from both sides, this is going to be minus G plus or minus delta G. And if I just select the bottom end of G, this gives me minus G min, right? So all I've done is just taken the nominal dimension of G, which has actually never been given. I'm subtracting out from the nominal dimension of G whatever tolerance is allowed in G, and that gives me G min. And this minus sign comes from the fact that I subtracted G from both sides. So it is eliminated here, and it appears over here as minus G min. By the same token, for number 3, equation number 3, I'm going to focus on G max. So I'm going to isolate this guy. I'm going to bring him over to the other side of the equation. So this is going to be, instead of 0, it's going to be minus G plus or minus delta G in parentheses. And then I'm going to, in this case, I'm going to select the bilateral dimension that's the positive one. So it's going to be the nominal dimension plus whatever tolerance is allowed in that dimension. And this is going to give me minus G max. And because I've subtracted this vector G plus or minus its tolerance from both sides of the equation, that goes away. Okay, so let me pause there for a second. Everyone okay with the math that I just did there to get these in terms of G min and G max?
Yep.
Okay, great. Okay, so now here's where things get a little weirder. So now that I've got equation 2 in terms of G min and equation 3 in terms of G max, I have to decide which tolerance I'm going to select on each of the nominal dimensions, whether I want to select the tolerance that's added or the tolerance that's taken away from the nominal dimension to achieve my G min or my G max. And so the way that I do that is I look back at the drawing, and there's the way that Dr. Nimi would have you do it, which is to look at every single part and decide whether you're going to use the high or the low bilateral dimension or bilateral tolerance. For me, I have a trick which always works, and it makes it a lot easier, which is to pick one part that I can actually visualize how changing that part would manipulate the dimension that I'm interested in. And then once I select the appropriate tolerance, that whether plus or minus, all the other tolerances will fall out in such a way that the sign sitting in front of the tolerances is the same. So it's a little trick, but it makes this a lot easier. So there's sort of like the right way to do it, which is like the long and painful way, which we can go through. But then there's the trick. So I'll show you guys. Well, let's do both. Let's do the long and painful way first, and then the trick second, since we have 2 equations to work with. So for number 2, I'm looking for G min. And so what I want to do then is in all of these tolerances that are left, I want to select either the plus sign or the minus sign in such a way that it gives me, the end result is G min, right? Where G min is the smallest gap here. And so let's just go through and start looking. So if I look at T, what's T? T is the terminal. Okay, right. So T is the terminal, which basically starts here. And t is this vector. And so if everything else being the same, if I increase t, the vector t, it pushes the core out a bit to the left and it decreases the gap, right? And that's Gmin, that's what I want. And so I'm gonna circle the plus sign here on t to indicate that I want to add delta t to t in order to get myself to, whoops, oh no, I circled the wrong place. Ah, okay, there we go, sorry. I circled equation 1 and I meant to circle equation 2. So ignore that circle, that's wrong. There we go, circle 2. So then the next one is the core. Can anybody tell me, looking at the core, whether I want to add delta C or subtract delta C from the core to get Gmin? Add, yep, exactly. Okay, and why? Well, because the core starts here and ends here. So if I make the core longer, that decreases the gap. And so by making the core longer, that's add delta C. I'm not going to worry about the gap because I moved that to the other side. Okay, so how about H? H is the housing. Do I want to, all other things being equal, do I want to increase or decrease the housing vector to change the size of the gap to Gmin? This is where it gets tough. This is why I have a trick, by the way. Decrease. Yep, there you go. Right. So all other things being equal, if I decrease the length of the housing, what that'll do is bring this surface at the edge of the gap closer to the core. So I want to decrease the housing, which means I'm going to select the negative sign there. How about for the where is it? The seal. Let's see, because the housing, yeah, the housing runs to the seal. So for the seal, all else being equal, do I want to increase or decrease the seal thickness or width? Yeah, okay. I see a couple of people saying increase. It's increase, and this one is the hardest one to visualize, and this is why I have a trick for this. So yeah, it's increase, and the way to sort of see that is everything else being equal. If you increase the seal, what it'll end up doing is pushing, depending on how you look at it, either pushing the housing away from the core or pushing the core. Oh, hang on, I've got that backwards. If I increase, yeah, right, okay, sorry. If I increase the seal, see, even I get confused, which is why I have a trick. If I increase the seal, what it'll do is end up either pushing the housing towards the core, that's what I wanted to say, push the housing towards the core, or if you look at it from the other direction, it'll push the core towards the housing. So either way, increasing the seal pushes these two parts together and decreases the gap. So it is actually plus. And then the insulation, which is, let's see, the insulation is this part here. That one, I'll just tell you because it gets complicated. So that one is decrease, is minus. Okay, so we have all those identified for G min. And I'm gonna rewrite these on the next page, just with the pluses and the minuses isolated. But we still have to do G max, right? So we still have to do the second one. And okay, you could look at it and say, yes, okay, it's just the opposite, right? So if I've got a plus here, I've got a minus here. If I've got a plus here, a minus here, and so forth. And that's true. But also, this gives me a great opportunity to show you guys the trick, which is I pick the part that's easiest to visualize and figure out whether the tolerance has to be added or subtracted from that particular nominal dimension. And then I look at the sign sitting in front of that particular nominal dimension and tolerance combination. And it turns out for this to work that all of the tolerances have to have the same sign sitting in front of them. That's a little kind of neat little trick. And so if you do it with one part, you can make it go really fast. And so you guys will see it, you end up with the same result. So I'm going to look at the core, right? So it's easy to see if I've got the core that starts here and ends here, and I'm now going for G max, the maximum gap. I want the core to be as short as possible, which means I want to take the core nominal dimension and subtract the tolerance in that dimension. So I'm going to subtract. So a couple of things. One is, yes, it was plus here for G min, and it's going to be minus here for G max. So that makes me feel good. And now if I look at the end result of the sign that's going to show up in front of the tolerance in the core dimension, it's going to be minus, right? Because I've got a plus here and a minus, so a plus times a minus is a minus. And so I want to make sure that I've got a minus sign sitting out in front of all of my tolerances. And so here it's easy, right? I've got a plus sign kind of implied sitting out in front of T. So a plus times a minus is a minus, so I'm going to circle minus there. Here, I've got a minus sign sitting out in front of H. And so I want all the signs to be the same, right? So it's got to be minus and minus. So here, I want a plus sign. Whoops. Oh, I want a plus sign because a minus times a plus is a minus, right? So I've got a minus here, I've got a minus here, and I'll end up with a minus here. This guy is the same, right? I've got a plus, so I want to circle the minus, and here I've got a minus, so I want to circle the plus. And what we end up with is it works out, right? So by just looking at the core, which was easy to visualize, and setting that one, and then determining how all these other tolerance signs had to shake out, I end up with exactly the opposite of what I had in equation 2, which is what I want, right? I had a minus here, a plus here, a plus here, a minus here, a minus here, a plus here, a plus here, a minus here, a plus here, a minus here. So it works out correctly. Even, I'm looking at it sort of simultaneously in several different ways, but you can see that it works out either way. So the trick, again, is to find the component that you can very easily visualize, figure out the sign of the tolerance that has to be sitting in front of it, and make all the other tolerances work out so that they have the same sign. So anyway, now you know the trick. Don't tell Dr. Nimi that I told you, because he doesn't like that I show people this. Okay, so any questions on how I set those pluses and minuses? Nope. Okay. Boy, I had a whole stack of paper. Oh, here it is. Okay. So let me bring in a fresh sheet of paper here, and we'll kind of rewrite these and simplify them at the same time. So I'm gonna end up with two equations. The first one is going to be my G min equation. So I'm going to say minus. Oh, and let me not do this in red. Let me do it in black. So I'm going to say minus. So I'm just writing equation 2 over again. So this is equation 2, but I'm writing it and simplifying it simultaneously. So I've got minus G min, and this is going to be equal to, now I can go through and pick everything correctly. So it's going to be T plus delta T plus C plus delta C. I don't have to worry about G because I move that to the other side, minus H plus delta H plus S plus delta S minus I plus delta I. Yes, and that equals G min. Okay, and so everyone follow what I did there? That's just distribution, multiplication, distribution. Seems like everyone's okay. All right. So now I'm going to write another line now. So I'm going to write minus G min. And I'm now going to put all of the nominal dimensions together and all of the tolerances together. And you'll see why this is another time saver. So it's going to be T plus C minus H plus S minus I. Did I get them all? T, CHSI. Yep, okay. And then I'm going to add delta T plus delta C plus delta H plus delta S plus delta I. Okay, so a couple of kind of neat things come out of this. So one is now that I've written this, it's very easy to just copy it over again for Gmax, right? Because the only thing that's changed between Gmin and Gmax, as you guys will see, is this sign sitting in front of the tolerances. The other thing that I want to check here is just a sanity check, is that all the tolerances are the same sign, right? So plus, 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 plus. Yes, they are all the same sign. And so this checks out. So that's just a check to make sure that you've done the math correctly. So now if I write number 3, write equation number 3, I'll write it out in all of its glory, but then I'll do it quickly. So this is T, and it's going to be minus delta T plus C minus delta C minus H minus delta H plus S minus delta S minus I minus delta I equals Gmax. And then here you'll see if I write it again super fast, right? I'm literally just going to write this over again. So it's T plus C minus H plus S minus I. I didn't even need to look because I'm just copying this down to here. And then here I'm just copying again. And the only thing that changes is instead of the plus sign, I've got the minus sign sitting in front of all the tolerances because they have to have the same sign. So if I just write a minus sign in front of them and then distribute that minus sign, I end up with that. Whoop, okay, there we go, end up with that. So yes, they all have the same sign. This matches this with the exception of the minus sign, so I'm all set. Okay, so let me pause there for a second. Any questions on how I wrote these equations? Okay, sounds like we're okay. So remember, my goal, at least in this first part, my goal is to find Gmin and Gmax. And the reason I want to do that, if we go all the way back to the problem statement here, is remember that we're being told, well, okay, so we did A, right, which is set up the equations for your tolerance loop in vector format. So that is basically everything we've done up until this point. And now for, this is maybe part B, determine the minimum and maximum gap expected from your tolerance loops, right? So now we're working on part B, finding the minimum maximum gap. We have the equations, we just have to plug in the numbers. So here's where I'm going to go back to my trusty, oh, I'm going to run out of room. Okay, let me see if I can do it this way. Yep, there we go. Okay, I'm going to go back to my trusty set of equations here. And so for minus G min, so I'm just doing equation 2 again. T is 13 millimeters. C is 44 millimeters. H is 40 millimeters. S is 5 millimeters. And I is 23 millimeters. So all I'm doing is just, let me bracket this. So I'm just taking this guy and I'm plugging in the numbers from here into there. And then let me write the tolerances. So I've got plus and delta T is, let's see, and I have to be careful. Okay. So hang on. Let's be careful here for a second. So remember, these are all bilateral except for C. So except for this one, right? I've got plus 0.22 and I've got minus 0.0. And so when I do C over here, I have to remember which one it is that I'm doing. So for 2, C should be the positive dimension, and for 3, C should be the minus dimension. So we'll just remember that when we get there. Okay, so So delta T in both directions is 0.065. Okay. C, remember for equation 2, I'm adding, right? So I'm adding, which means I need to take 0.220 as the dimension here. And you guys will see when I do Gmin how that changes. So it's 0.220. And then H is, what's H? 0.200. And what is S? S is 0.025. And I is 0.115. Okay, and it's all millimeters. All right, so when I plug in the numbers, well, here, let's just do it live in real time. So here's my, whoops, I should probably get a better calculator than my phone, but here's my phone, is our calculator. Okay, so 13 millimeters plus 44 millimeters minus 40 plus 5 minus 23 gives us -1. Okay, so we've got -1 millimeter is the sum of all of our nominal dimensions. And then to that, we're going to add, let's see, oh, wow, the stock market's doing good today. That's why I don't like using this calculator. 0.65 plus 0.22 plus 0.2 plus 0.025 plus 0.115. Okay, so I'm adding them all up and I'm getting plus, so these are now the tolerances, 0.625. Okay, and so now if I solve this for Gmin, I'm just gonna say Gmin is equal to 1 millimeter minus 0.625. So all I've done is just taken this minus sign and distributed it through. So 1 minus 0.625 is, okay, 0.375 millimeters is Gmin. So we've got that one solved. Okay. Any questions on the math underpinning how I got to Gmin? This is mostly algebra, but just want to make sure everybody is good. Any questions on that one? Okay, sounds like we're good. Okay, so let's do equation 3, and you guys will see there's a subtle difference here. So equation 3, recall from up here, is minus G max is equal to T plus C minus H plus S minus I, and now minus delta T plus delta C, I'm just copying it again, delta H, delta S, delta I, and let's put in the numbers. So if I put in the numbers here, this is exactly the same as this. So I'm going to end up with -1 millimeter here. But then over here, I've got to be careful because I've got that different dimension, right? So C on the negative side is 0, and on the positive side was 0.22. So I've got to be careful. I can't just rewrite the dimension for the tolerances over again. I can write most of them over again, but not all of them. So this is going to be 0.065. Here's my delta C. This is where I have to be careful. This is plus 0.00. Delta H is 0.200. Delta S is 0.025, and delta I is 0.115. And the thing that I really want to emphasize that we have to be careful about is that number and that number. Whoops, and there we go. So that number and that number. Here, again, it's 0.22 because the plus unilateral dimension for delta C was this value. Here, it's 0.00 because the minus unilateral dimension for C was 0. So those two are different. And the way that you, again, keep track is if you go back to your original equation and look at what you circled for C, right? So for G min, I circled plus, and for G max, I circled minus. And so for G min, I'm choosing the plus value, and for G max, I'm choosing the minus value. So that's why there's that subtle difference. But if you don't do that correctly, you end up with the wrong answer. Okay, so let's punch in the numbers here and see what happens. So I'm going to have 0.065 plus 0 plus 0.2 plus 0.025 plus 0.115. Okay, that gives me 0.405. So this is going to be minus, lots of things to keep track of, colors. Okay, so minus G max minus 1 millimeter, which we got from before, and now minus 0.405. 0.405 millimeters. And let me just triple check. Yes, okay, yeah, right. So when I solved this before, that's what I got. Okay, so, and this should be an equal sign. Okay, so now, I did something wrong. I made this an equal. Oh, I need the minus sign sitting here. Okay, I forgot to write the. Okay, I got it. I wrote the minus sign. I forgot to write the equal sign. I got rid of the minus sign by accident when I wrote the equal sign. So now we're all set. Okay, so now I can solve this for G max, and what I get should be that G max is equal to 1.405 millimeters. Okay, so. Questions with how I got G min and G max? Good so far. Okay, cool. All right, so if we go back to the original problem statement, I've just done B, right? So determine the minimum and maximum gap. Oh, sorry, there you go. Determine the minimum and maximum gap expected from your tolerance, show the work. So I've just done that one. And now I've got to do the third part, which is the gap must be between 0.5 millimeters and 1.5 millimeters for proper function. What changes, if any, would you make to the component dimensions or tolerances? Okay, so our gap has to be between 0.5 millimeters and 1.5 millimeters. That's the specification to ensure that combustion is happening properly when our spark plug fires. Anybody see the problem? Anybody see why the spark plug is not firing?
G min is too small.
Yeah, exactly. There you go. Right. So here's G min, right? We just calculated it. And remember, again, this is an assembly line process. This is a manufacturing process. And so some of these parts are coming off the assembly line and being assembled in such a way that the gap is in fact between, you know, this minimum and this maximum. So some of these spark plugs are working, but some of them are not. And the ones that are not working just happen to be the ones that the combination of the parts is such that the extreme tolerances, when they stack up, get us to this G min that's outside of the specified range. And so what's actually happening is the spark plug is firing, the spark is jumping, but there isn't enough room in the spark plug, there isn't enough room in this gap for the flame to propagate outwards and cause the full combustion process to happen. And so so we need to somehow increase the gap. And so in part C then, we found that there's improper function because the lower bound is too small. And so we've got to now go back to our manufacturer and we've got to say, hey guys, you need to adjust your tolerances on your parts, or adjust your nominal dimensions on your parts so that your spark plug functions correctly. And so what suggestion would we make to them? Well, there's effectively an infinite number of possibilities, right? Like you could go through and you could change nominal dimensions, you can go through and you can change tolerances, but the one that really makes the most sense, if we go back to our chart here, is to remember that all of these dimensions are bilateral except for the core, right? And so the company is actually set up to achieve these bilateral tolerances on the terminal, the housing, the seal, and the insulator, and they're set up to achieve unilateral tolerances on the core. And so the best way to do this is to just change one of these tolerances. So just change one of the tolerances in the core, and that produces the minimum amount of change, right? It's the minimum amount of change in the overall process. Certainly there are other correct answers, but the easiest one is just to change one of these dimensions. And the dimension that we want to change, since G max is fine, right? G max is 1.405, which is less than the maximum bound. The one that we want to change is G min, the one that's associated with G min, and haha, lo and behold, the one that's associated with G min is this really big tolerance on the core, right? So this positive tolerance on the core, this 0.220. And so we now transition from kind of a type 2 problem, like I described before, into a type 3 problem, which is we now know kind of what it is that we need to preserve, and we have to change either the nominal dimensions or the tolerances or both in order to preserve that function. So the reason that I like this problem so much is that it's sort of both the type 2 and the type 3 that I talked about in the lecture. Okay, so what do we do? How do we do this? Let's get a fresh sheet of paper. Let's find my paper to begin with. Here it is. Okay, so I'm gonna grab a fresh sheet of paper, and so for C, for part C, we know that the gap never exceeds 1.5 millimeters, but it can be smaller than 0.5 millimeters, which causes misfire. So the problem is mechanical instead of electrical, and what we need to make this work, we need G min to be equal to 0.5 millimeters, right? Not smaller than, but at least equal to. And so our solution is to adjust the core to accomplish this functional feature dimension. So I've got all the tools that I need. I just have to hop right back into my equation. So I'm going to hop right back into here, my G min equation. So I'm just going to write it over again. Oh, okay, let's write it over again. So we know that minus G min is equal to T plus C minus H plus S minus I, and plus delta T plus delta C plus delta H plus delta S plus delta I. 1, 2, 3, 4, 5. Okay, got it. All right. So here's that same equation again. I am not going to mess with any of the nominal dimensions, and the only tolerance that I'm going to mess with is the core tolerance, right? This one, because that's the one that I'm selecting to change. And so as a result, I've already got all the numbers, right, with the exception of this guy, so I can just solve this for delta C. So G, this is just minus, I want it to be 0.5 millimeters. And that equals, if we remember going through all this worked out to be minus 1 millimeter. So the sum of all these nominal dimensions is minus 1 millimeter. And then let me put these guys in. Okay, this one, delta T is going to be 0.065. Delta C is the one that I'm solving for, so I'm going to leave that alone. Delta H is 0.200. Delta S is 0.025, and delta I is 0.115. Okay, and now I'm just going to solve for delta C. And at least when I plug in the numbers, it works out to be 0.095 millimeters. And you guys can run through and punch in the numbers and see if you get what I got. But that's when I solve for delta C. And so ultimately what I'm going to recommend then to the manufacturer of these parts is to adjust the core dimension. And when I say core, this is the part that's called the core, to its nominal dimension, which was, oh, there it is. So the core's nominal dimension was 44. The unilateral dimension that I did not change was on the negative end, which is 0. And the one that I did change was on the positive end, which is 0.22. So I'm going to change it to 44 millimeters now, plus only 0.095 and then minus 0.000 millimeters. So all the company has to do then in making this one change is simply simply adjust in all of their drawings this one upper unilateral dimension on the core part to make that more precise, and that should solve the problem. So if we head back to our problem statement, let's see, what changes, if any, would you make to the component dimensions or tolerances? Well, I messed with the core tolerance and I solved that one. And we've got that one solved too. So I've got this one completely solved, I hope. Any questions on how I did it? Okay, seems like everyone's okay. So let's just preserve this by let me stop the recording.